Hi, everyone. My name is Lan Wu. I'm from University of British Columbia. Thank you for organizing this session. Sorry that I'm unable to attend this conference in person because of the conflict with the final exam for my course and the visa issues. So today, before I start my presentation, I will share my screen. So here is, let me see, I'll make it full screen. Okay, so my talk today is the joint model of longitudinal data and the survival data with censoring and outliers. So we consider joint model for longitudinal survival data, whereas longitudinal data may be left censored or may contain outliers. So our research is motivated from HIV vaccine studies. And the objective of the study is to identify immune response by markers marked longitudinally, but the data may contain outliers and censoring, and check to see whether these biomarkers are associated with the risk of HIV infection. So analysis of this content are complicated by some of these issues. The data, the longitudinal data may be left censored due to detection limit. And of course, there are maybe different type of variables, some continuous, some binary, and also another issue is outliers. So here is the example of the data set. Here's the, for example, CR4 for immune response biomarker measurement. So the data shows periodical patterns. A solid line represents the eventually infected patients, and the dotted line represents uninfected patients. And we want to see whether this longitudinal trajectories are predictive for the risk of HIV infections. So we propose a joint model for longitudinal data and the survival data to address this issue simultaneously. So we use mixed effect model to model the longitudinal data, and use a Cox model with shared learning effect to model the survival data. So for the censoring longitudinal data, sensor longitudinal data, our method do not assume any distributions for the unobserved sensor data. So the idea is to treat the censored value as a point mass at the threshold value. Then we use a method similar to zero inflated model for steady inference. So in addition to censoring, a second challenge is modeling several longitudinal variables of different type. For example, some may be continuous, some may be discrete. And we propose to use mixed effect models and assume that the models share or correlate random effects, which incorporates association between different types of longitudinal variables. So a third challenge is to address potential outlier in longitudinal data. So for longitudinal data, the outlier can be classified into two different types. E outlier is the outlier among the repeated measurement within individual, and the B outlier is the outlier individuals in the samples. So we treat the outlier in different ways. So for the B outlier, we assume heavy tail multivariate T distribution and use M estimate for the E outliers. So this is the example of E outlier and B outliers for longitudinal measurement. And for survival data, we consider a Cox model and link the survival model to longitudinal model through shared random effect. This may be reasonable because the random effect in the longitudinal model represents the individual characteristic of the longitudinal process. So the risk of infection modeled by Cox model may be associated with these individual characteristics. So here are some notations. So we consider two different type of variable, one continuous or one binary. denoted by Yij and Yik. So Y is continuous, but subject to left censoring, and J is binary. Then for the set, the binary longitudinal variable set, we consider a generalized linear mixed model is a logistic regression model with a random effect. Random effect here as a B is a factor assumed to follow normal distribution. So this generalized linear mixed model also includes the linear mixed effect model as a special case. Then for the uncensored continuous longitudinal data, we consider linear or nonlinear mixed effect model. So here, this Yij. So G is a known but possibly nonlinear function, and B2I is another set of random effect for the continuous longitudinal data, and epsilon is error term. And for the censored longitudinal Y value, we propose the following model. So you have a detection limit D, which is for Y value below this D, you cannot observe. So these are censored. So we can have a sensorily indicate Cij to indicate whether Y value is censored or not. Then we model this indicator data by another logistic regression model with random effect. So you have another set of random effect, B3I. Then this 3 model, the 2 longitudinal models for binary variable and continuous variable, and the censoring model, we link them together by assuming that the random effects from these 3 models are correlated. So this incorporates associations between different type of variables. For the survival data, we let T, these are standard notations, infection time, and also this censoring time, TCI. Then what you observe is either event time, infection time, or censoring time. And also have we can have indicator variable data to see whether the individual is infected or not. So here, this indicator variable, of course, is different from the longitudinal data. Earlier we introduced indicator variable for censoring or not, but this one is this indicator is for the whether you observe events or not. So there are 2 types of censoring. Then for the survival data time to infection, so we consider this Cox proportion Hansen model. And here in this model, XSI includes the covariance, and the BI, this BI is from the 3 longitudinal model. So recall that we have this BI is the random effect from 3 models that we discussed earlier. Then we link the hazard to the random effect in these 3 models. So here lambda is a key parameter which link the longitudinal characteristic to the risk of HIV infection. Then we propose a joint likelihood approach. So the joint likelihood for all the observed data, then you can write down the likelihood function, and you indicate out the unobserved random effect. So we have 3 longitudinal models and a survival model. Then you integrate out the random effect. This because this random effect, the factor of random effect comes from 3 longitudinal models. This integral is high dimension, and the computation can be quite challenging. So for the E outlier in the Y data, we use M estimator. Well, it's a well-known M estimator to downweight the influence of outlier in the estimating equation. So this is a standard estimating equation for M estimate. And here phi C is a Hilbert function. It also has depend on a value of C. Then for the B outliers, outlier in the individuals, we assume the random effect follow a multivariate T distribution with degree of freedom phi and covariance mass sigma. So this is a multivariate T distribution to adjust the outliers in individuals. So previous one, the outlier is adjusted by M estimator for E outliers, and for B outliers, we adjust outlier by a T distribution. Then for both distribution, you can, for the Hilbert function, you can choose turning point C in a usual way. For example, usually choose 2 or 1.6, depending on how robustness you want it to be. And also for this multivariate T distribution, the degree of freedom also reflects the degree of robustness. So we have this joint likelihood, as shown earlier. This likelihood is a high dimension and intractable. So typical approach is use the EM algorithm, but the EM algorithm can computationally very slow and even some non-convergence. Similar for numerical integration method like Gaussian quadrature method. So here we consider a process method based on the so-called H likelihood developed by Lee in a series of papers. So this H likelihood is computation more efficient, much more efficient, and is may be viewed as a Laplace approximation to the integral in the likelihood. And for the vaccine data, because they are periodical patterns, so we introduce the different time variables. Tij is the time from beginning to study to current schedule values, and Tdij is the time from the most recent immunization to the current measurement time, and also the time to 2 consecutive vaccine administration. We have introduced another time variable, so 3 time variables to describe. So the model for the vaccine model you can write this way. So we have 2 longitudinal biomarker measurement. One is Zij, which is binary, and another one is Yij. So the sign function is introduced to roughly models a periodical pattern of the longitudinal process, and you have random effects in the models. Then C is a sensory indicator, because sometimes the biomarker values may not be measured at the scheduled time. So sometimes we don't know whether it's a sensor or not. So we propose a model to model the sensory process. And then the last one is the Cox model, which we have covariance in addition to the random effect. So here, the lambda 1, lambda 2 parameters are important because they represent how the longitudinal processes are associated with the risk of HIV infection. So the analysis results is shown in this table. So you can see that the result, so we focus on the key parameters, lambda 0, lambda 1, lambda 2, and we consider different robustness, C equal to or infinite, that becomes a normal distribution. And C equal to 2 also when the random effects, follow different kind of distributions. So C is a Hilbert function. It's a value in the Hilbert function, which is used to model the outline in the repeated measurement. And the random effects are assumed to follow T distribution with different degree of freedom. So the results show that they show some kind of different results based on how robust the model are. So our main objective of this analysis is to track whether the parameter estimate standard error affected by potential outliers in the longitudinal data. So we can see that the robustness and robust method and the non-robust method produce somewhat similar estimates than the errors. So this at least suggests that the impact of potential outlier may be small in this setting for this data set. Then we conducted a simulation study to evaluate the proposed method. So simulation repetition is 100. So we assume different degree of robustness by choose the degree of freedom in the t distribution and also the value of c in the Hilbert functions. So we consider bars, relative bars in percentage and the mean square errors in the usual way. So here is the simulation result with 5% B outliers. So we have estimated standard error and NR is non-robust and R1, R2 are different degree of robustness. And as you can, and also standard errors. So in this setting, you see that the parameter of main interest lambda 0, lambda 1, lambda 2. So they also give somewhat robust estimates, even though the degree of robustness may be different. And the bars and the mean square errors of these three methods here seems comparable. And this is a simulation result with 5% E outliers. So in E outline means outline is a repeated measurement within individuals. So you can also see that the results are somewhat similar. And this indicates that the actual likelihood method we use also have good performance. Okay, so the conclusion from simulation study is that the proposed robust method works well, and preferred early result is preferred to non-robust method. Here, NR means non-robust method. It gives you a higher mean square error and the higher bars compared to R1, R2, which these are the robust method. So the robust method perform better in simulation study. And the advantages of the robust method are more substantial for E outliers and B outliers. So this table is for E outliers. So the robust method perform better than the non-robust method. This is B outline, and the result seems similar for non-robust method and robust method. And the same, the standard error also seems somewhat underestimated. So we can use, if we want more reliable standard error, we probably can do a bootstrap method to get a more reliable standard error. And the data analysis, in the data analysis section, we show that the longitudinal immune response seems highly associated with the risk of HIV infections. Okay, thank you very much. That's the end of my study, end of my talk. Thank you very much. Sorry again that I have to present online. Okay, thank you.